Okay, it seems like everybody is good to go. So let's get started with our webinar. Here on this slide, you can see our email addresses. If anything comes to mind after the webinar, you can send us an email. Also, if you have questions after the presentation, you can feel free to type your questions right here in the chat box. Okay, so let's get started with the next slide. So unfortunately, the map of upstate New York is just showing up as a big black rectangle here. But in fact, if you look at a map of upstate New York yourself, you will find that about 2.5 hours north of the city by driving or by train, by Amtrak, there's a place called Albany, New York. That's the capital of New York State. And that is very close to Troy, New York, the location of Rensselaer Polytechnic Institute. We're trying to point out on this map that we're within driving distance, within a few hours of Boston, as well as about 3 hours south of the city of Montreal, if you drive fast. We're surrounded by the Adirondacks and the Catskills, which are scenically very beautiful areas. I think it's a great location if you enjoy outdoor activities, and if you'd like to maybe on the weekend do a city trip down in New York or up to Montreal. There's one photograph here of our campus showing one of our premier buildings. It's the Center for Biotechnology and Interdisciplinary Studies, or CBIS, as people sometimes call it, or just the biotech building. This houses some of our state-of-the-art core facilities in the areas of biotechnology and chemistry and many other areas. So that's just a summary of where we're located. On the next slide, we have some information about the Institute. It's very old. RPI was founded, which is a good thing. It was founded in 1824 by Stefan von Rensselaer. It's considered to be the nation's oldest technological university. So Rensselaer was an industrialist, and he wanted people to be educated in application of science to everyday life. So that's what we do. We are within the School of Engineering at RPI, which is, I think, one of the biggest components of the whole institute. And it was quoted by the Princeton Review that we're simultaneously the oldest technological school and also one of the most modern. So this is a place where students and faculty from all over different areas come together to work on and solve big problems that have a big impact on society. So within our school, we have 7 different departments with about 140 faculty and somewhere around 430 PhD students at any given time. There are various different areas. So we have engineering for the life sciences. Again, in the upper right-hand corner of the slide shows you a picture of the CBIS building. We also have a really strong foundation in big data and computation with our supercomputer. We're known for advanced materials, systems automation and control, as well as energy and sustainability-based research. Okay, next slide. Here's some photographs of all our faculty with their names, which we tried to fit in between the pictures, but you can see, I guess our names are too long in many cases. But these are all the core faculty in material science and engineering. On the left-hand side of the slide, you can see Paolo Pawlinski. He's currently our department head. And just next to him is Robert Hull, who is the director of our materials center on campus. And you can also see the participants on this panel are also here: Chaitanya, Li Ping, Jian, myself. And so we have 17 faculty members, about 65 graduate students, although of course the numbers fluctuate from year to year, about 150 undergraduate students, and 7 staff members that includes administrative and technical staff people. And on the next slide, we also mentioned that beyond our core MSc faculty, we also have some faculty with joint appointments from other departments like biomedical engineering, physics, chemical engineering, and so on. Our faculty are members of various material research programs institute-wide, and we're affiliated with numerous centers. These are either internally or externally funded major centers that bring together different researchers from different areas of expertise to all work on one core set of problems. In example is the Smart Lighting Center shown on the slide here. This is something that Chaitanya is involved with, and it's a very large-scale NSF-funded effort that's been going on here for many years. We also have a New York State-funded effort for future energy systems, as well as 3 other centers shown here that are based in RPI, the CBIS Center, the Center for Materials, Devices, and Integrated Systems. That's the one that Robert Hull directs, and also our Center for Computational Innovation. All right, so we have various different areas of materials research that we tend to focus on and where we tend to have particular strengths. They're all listed here, and we'll go through some examples of the various research opportunities that are available within each of these themes. The first one shown here is nanostructured materials. This has been a long-standing strength in the department, particularly with one of our most senior faculty members, Dick Siegel, who is the director of the Rensselaer Nanotechnology Center for many years, which was funded very strongly by the National Science Foundation and brought in a number of really great faculty, including some of the other people who are listed there. Polymer materials, which is my area of expertise, as well as polymer nanocomposites have long been an area of interest with people like Linda Shadler and Rami Azizic, as shown here. We also have an area in the materials biology interface. This is something that Dick Siegel and Linda Shadler and people like that were working on for many years. And when I joined the faculty a few years ago, also started to make contributions in this area, focusing on how material science interfaces with living systems. We also have energy and electronic materials as major strength areas with people like Robert Hull, Daniel Gull, and Professor Ramana as well. And we have now Jianxi, who joined us recently, who's making a really major impact on these areas as well. One of the most unique strengths of our department, in my view, is that we have a very strong glass science field, which has been an area studied by Professor Tomozawa for many, many years. He came here back in the 1970s and still to this day is a very active, energetic researcher in this area. We also have Li Ping and Fong and Yongfeng Shai who make contributions to this area, continuing the tradition of Tomozawa. There's also a very strong connection with the Corning Glass company, which is only a few hours west of here in upstate New York. And so many of our alumni who work for any of the professors in this category will go to work as employees of the Corning company after graduation. Physical metallurgy and processing is an area that has been, from the beginning of material science, has been one of the biggest and most important areas dating back to the World War II era and perhaps even earlier than that. And this is where RPI material science history really had its start and where we had our biggest impact historically when the department was coming into its own originally. Now the final one here is actually one of the most exciting areas within our department and also across campus, because we have a number of faculty members who are interested in materials from a computational and theoretical perspective, including our newest hire, who isn't here now, but Ravi Shankar Sundararaman is our newest hire, and he is bringing in a new set of skills in computation that really help people understand from a theoretical perspective how materials work. And so all of the people listed here in this area have made major contributions to computational material science. Okay, so with that, I think we'll go into each of these areas in sort of a general overview, and Chaitanya is going to take over.
Right, so since these overlap very strongly with the areas that I'm very interested in, I'll just talk really briefly about some of the efforts that various faculty have in nanostructured materials and soft matter, which would be both polymers as well as biomaterials. And I won't be able to do complete justice to every faculty's interest, because some of the faculty are so diverse in some of the things that they do that we'd be here all night, and probably for you if you're in China or some of the other countries all morning. So we don't want to do that. So what I'll do is just give you an overview of sort of the things that it connects with and some highlights from some of the research that our faculty are doing. As Ed mentioned earlier, Rensselaer really has been at the vanguard of nanomaterials for quite some time. Since the large increases in funding that happened in the early 2000s, we've had, some of our traditional nanomaterials actually started when Dick Siegel, who used to be the director at our National Lab, came to RPI, and he was the department head, and he got an NSEC, which was a center basically for nanostructured materials, and that sort of catalyzed the formation of the Rensselaer Nanotechnology Center. And so, in addition to that, we accumulated a critical mass of people doing exciting research work that was across all aspects of nanostructured materials, right from the nano-bio interface, John Dordick, Dick Siegel, people working on the nano-bio interface, right up to people like Nikhil Puratkar working on flat materials. And we have a very strong tradition. In fact, we have a lot of people, not just in material science, but in physics and other places, working on these various topics. And one of the things that I'd like to point out is, and this is true across all the disciplines that I'm going to be talking about, nanostructured materials, polymers, biomaterials, and the other things that Professor Shah and Professor Kwang will be talking about, is that there is a lot of collaboration amongst the faculty. And this is both just individual connections that people make, as well as things that are catalyzed by the centers that are at RPI. For example, Mike Deegan, who's here, works in my group, but he's also co-advised by Dr. Linda Schadler, and he also speaks fairly regularly with Bob Kardasek, who's the director of the lighting center. I don't know if I'm stealing some of your thunder. But the idea is that there are systems in place that catalyze and ensure that high quality research happens not just through the interests of the individual faculty, but happens at the intersection of their interests as well. And this is true, if you go to the next slide, this is true as well in polymers and nanocomposites. And if you look at the figure on the right, it looks like just a bunch of arrows, but what is, for some reason, in the conversion from the PPT, which looked really nice, into the PDF, that happened a little before we came for the webinar, we lost in translation a little particle that had two types of polymer brushes on it. And this is an example of some of the groundbreaking work that happens at RPI. Right? So this was started at, and although you can't see the picture, there's a lot of people who care a lot about some of the papers that are involved in this research. So this particular research that I'm referring to was started by Dr. Linda Schadler, and she essentially figured out a way to make sure that nanocomposites would have mechanical integrity while retaining a lot of the advanced properties that the nanomaterials bring to nanocomposites. On the left, you have a figure from my research, which is related to a pet topic of mine, which is trying to image materials with visible light while breaking the diffraction barrier at the nanoscale. And I'm particularly interested in trying to unravel questions in self-assembly, as well as using these concepts related to lithography and nanofabrication. But once again, just like we saw in the case of the nanomaterials, there are various centers that Dr. Schadler and I and other people like Ed, who are in polymers, Rami Ozizik, Dick Siegel, who are working in soft matter and polymer materials. We connect not just with each other. For example, Ed and I have a recent proposal that we got funded by the NSF. Not only do we collaborate with one another, but we benefit from the various facilities that are available at RPI. For example, the Center for Biotechnology and Robert Hull's Center for Materials, Devices, and Integrated Systems. So if you go to the next slide, this is the other aspect of materials biology, of materials at the biology interface. And once again, in keeping with the themes that I've sort of been just beating you over the head with, the idea remains the same, right? We're doing cutting edge work. This is work that comes out of Ed Palermo's lab related to, Ed, do you want to say a little bit about it?
Sure. We're working on looking at polymeric materials that can interact with biological cells at interfaces, and an example shown here here is a polymer structure that will kill bacteria on contact with the surface, and the surface one undergoes some chemical change in response to the presence of the bacteria and expel them from the surface. This is just one example of many things happening on campus here as far as research into the interaction between synthetic materials, whether they be polymers or other sorts of materials, with living cells.
Right, and I think just as a last time to reiterate what I've said, we're doing things that are across, that span things from really fundamental questions. Like, for example, in this particular case, Nick Siegel is looking at how proteins interact with curvature on the nanoscale, right? Because if you think of charged objects and you look at curved surfaces, those interactions can vary, and those can have very strong implications for the manner in which proteins behave, right? So there are questions that we're asking right on the scale that are fundamental scientific questions, and we go right up to questions which deal directly with devices and diseases. For example, in the case of the biology interface. For example, Professor Palermo has a project with Ryan Gilbert in the bioengineering department, and they're working on looking at the spinal cord and looking at specific conditions related to the spinal cord. So you'll find, so the things that I'm trying to convey are that we have a lot of interactions. We have facilities that allow us to work in these various areas, and we're looking at a span of questions. So with that, I'll hand over to Dr. Shai. They can talk about energy
and electronic materials. Thank you for your patience. So my personal research is energy and electronic materials. So we're happy to present some research associated with these two topics. So I'm going to start with this kind of week. So for energy materials, we pretty much cover battery, thermoelectrics, pyroelectrics, piezoelectrics, photovoltaics, all kinds of this energy conversion. For example, you see the left pictures, and that kind of picture is to use to solve one question. So what is the best material to make a battery? So we work on this kind of question. Indeed, that was produced by Professor Nikhil Krolika. So he's working on battery material, and one solution is this two-dimensional cathode knives. And we also ask what is the best material to convert heat or thermal energy into electricity? And Professor Ramnas, he's working on so-called bulk thermoelectric nanomaterials. One example is the bismuth selenide. So it turns out this material is very efficient to convert thermal energy to electricity. And how about a structure? He's also working on so-called heterostructure thermoelectric material to convert thermal energy into electricity. So this is two examples from Professor Nikhil Krolika and Professor Ramnas. So my personal research is to convert thermal energy to electricity, but in a different way. We work on pyroelectric materials, piezoelectric materials, and also work on photovoltaics, which is focused on the halide process. So that is our strength on energy materials. One more thing is Professor Robert Hall is also working on battery materials and focusing on the electron microscopy characterization of battery materials. So now let's go to the electronic materials. So we have 4 or 5 faculty members working on electronic materials covering nitrides, oxides, halides, decathlonides, and also pure metals. So one question we solve is, for example, in Professor Robert Hall's lab, the question is, what is the most efficient transistor we can build? We can beat current transistor. So one idea is this so-called quantum dots, and where you can probably manipulate the behavior of a single electron by gating. And this is one research project. Professor Robert Hall is working, and this is some quantum dots produced in his lab. So another kind of research associated with electronic material is perovskites for electro-optics and logical memory. So this is some material that recently rediscovered in 2009. And in past like 3 years, and its photovoltaic efficiency has increased from 3% to current 22%. There's a revolution in this field, and I'm very fortunate to work in this field. Rather than working on photovoltaics, we work on using this material for ventilators, light emitting diodes, and also logic and memory. And one question we solve is, can we build a UV laser? You know, there's no like much UV laser available in the world, and this material may have this potential to build like a UV laser. That's one part of my research. And we also have Professor Daniel Gao. He's working on two kinds of a field. One is nitrides, which is for hard coating. It sounds like more like mechanical behavioral materials. The other part of research is very fundamental. So why different metals have different resistivity? And his expertise is density functional theory and also like ion sputtering. So he created materials and he studied the transport property. And the last question we solve at RPI is, if we glue the material in a very thin like manner, for example, a 2 nanometer, 1 nanometer, what kind of a new property we can expect? This is a very fundamental and exploratory kind of research. And so we basically cover very application-driven and also very fundamental science-driven kind of a research associated with electronic materials and energy materials. So with that, I'd like to pass to.
There's a question last which picture can be met? Similar to the last picture.
I just have finished research in the last picture.
Which picture?
So which picture are you talking about?
You mean the nitride films?
Looks like.
He's talking about the
A soft substrate, state film structure. What's that? Soft substrate, state film structure. Okay, that sounds very interesting. Are you talking about the frost guys?
Or maybe we can take specific questions.
Yeah, we can take
Yeah.
questions at the end.
How about like this? We we can answer questions. After we finish, we are going to have a session just to answer questions.
Yes.
Right? Yes. Yeah. So awesome.
So as Professor Flemmer indicated at the beginning, RPI has a strong tradition in glass and amorphous materials, and so you may think glass is old materials, but actually it's also one of the in-memory materials and throughout human civilization history. And I believe everybody nowadays has some kind of smartphone or smart device in your pocket, and if you open up your phone, actually you have more than one layer, not just top layers. You touch and you swipe. You have quite a few layers inside. Each glass layer there serve different functionalities, and so the glass is not only in the hardware of the device we are using, but also is in the foundations where the reason you can hear us or you can communicate with your friends across the world or call your friends with crystal clear voice, because those signals are transmitted through optical fibers, which are made of very pure glass. And so those, without those glass fibers, we will not be able to have this webinar even today with people across the world at the same time. And also glass has been made thinner and stronger, and so the right-hand side of the figure there is not plastic. It's actually really made of inorganic oxide glass. It can make large scale, very thin, can do row printing of electronics on it to make a solar cell, really low solar cells, and also made them into flexible display. I think if you watch one of the latest Mission Impossible, you already know flexible display is going to come. Hollywood already told us. So that is enabled by those glass become stronger and thinner. So at RPI, we have Professor Tanzawa is the leading figures. So his long-term interest is to study the interface of glass with the environment, because glass often breaks because there's some defects or microcracks on the surface. Otherwise, glass is actually very strong. So how the surface evolving and changing with the environment is one of his key research interests. For my group's primary interest, I indentation pictures, the composition maybe just very tiny bit, but one just cracked very badly, another one you just make a dent like a metal without calling crack at all on exactly the same indentation conditions. Why is that? If you understand it, we can make glass much stronger and thinner. Another research thrust at RPI will be we try to synthesize normal glasses by using extreme conditions. So usually glass company made glass by quench as fast as possible to avoid preservation. But in our case, we try to also play the knob of pressure, which is not really used by glass companies. And we show that with pressure, you can make very unique structure and properties which you cannot obtain with conventional or thermal history control, which are usually used nowadays. And this is collaboration between material science and also Professor Bruce Watson, who is the adjunct professor with us. So he's expert in high pressure research, and we bring those expertise together to show that indeed, if we turn off the pressure law, we can get much unique glass. Yes, Stephen.
So we have a student, Qian. I guess she or he has been working on some glass plastic.
Oh, good.
That's very good.
That's great. That's great. So here is one of another areas we have a strong tradition, as Professor Flemmer indicated, is one of the areas where material science department build upon. We use it for metallurgy, I think, across the world, that was involved into material science and engineering. This is still a strong area at RPI, and we have Professor Lewis, Professor Duquette, and Professor Aim Chen working in these areas. So the problem we try to working on is ranging from most fundamental scientific questions, for example, how the precipitation and deformation will depend on orientation. So you basically start from those fundamentals, and all try to quantify how solid aggregate with boundaries by using atomic force microscope. And so we also move on to very hot research areas nowadays, basically interface engineering. So usually green boundaries is a weak areas, and how can you engineer the interface instead of just take those interface as is, what you can put some ductile thin layers, kind of glue things together to have both hardness and ductilities to make metals and alloys become stronger and tougher. So that is one area that we work intensively at RPI. And the lower and the right figure is nanoporous metal or metal foam, you may be familiar with. And those are the completely new way of thinking metals. Usually we think of metal as structural materials and magnetic bulk materials, but nowadays people actually make metal into form. And with those huge surface area and also mechanical strength, we can use them for very different applications, and use as for gas absorption, for catalyst support, for electrode, for batteries, or supercapacitors. This opens up a huge range of applications people usually did not think about it before. So this is also a very interesting areas our faculty are currently working on. And so the last one, actually, as you see at the beginning, in the department we have 17 faculty members. Last time I counted, we have 8 faculty members. Either 100% of doing modeling, or have somewhere between 50% to 100%. So we basically cover the whole spectrum from the most smallest scale atomic electronic level, such as Professor Munier, Professor Sonaraman. They basically try to use electronic structure calculation on stand, for example, in electrochemical reactions to help design better catalysts, for example. So we also have quite a few faculty work at electronic to molecular level simulations, and then move on to mesoscale to continuum level simulation. We have the whole range going from electron to macroscopic materials you actually can touch and test. So in the mesoscales, we use one color simulation simulation, try to understand how can we better design grains instead of have unique and homogeneous grain distributions. You can have gradient grain distributions that may have very unique properties. And also, as computational material science is relatively new areas to how to do calculations to get meaningful results. These areas is now quite clear. Not an experiment that standard procedure can follow. For example, if you try to do indentation, try to do 3-point bending test, we just follow some ASM standards. But in simulation, everybody pretty much still do their own. So we also have a group of people trying to establish different computational protocols, how to do different mechanical tests in computers, and so you can compare with experimental measurements. For example, we do those virtual indentation. You can directly compare with experiments, and once you establish those tools, you can save a lot of time, energy by doing those measurements in simulation instead of doing in real experiments. And similarly, you can use the tools to span a range of combinations of different processing conditions to understand why blood behaves differently. So in that sense, you can, because computer nowadays become so fast, you can easily access 100 of CPU or 1,000 CPUs a day, but I cannot afford 10 students. So I'm doing a lot of those virtual tests to establish those protocols. I think that is strong areas of RPI, and this is very, very strong areas across the whole landscape and time scales of our.
There's a question. Are you using 3-point bending for test mode to fracture toughness?
And in computation.
Yeah.
Is that what he's asking?
But then,
Are you using a group like that for testimony?
and that's too specific. We can go get back to that later.
Yeah. So we are going to answer this question after the introduction.
What is it? This is the last slide.
No, we'll have a little bit more about general application.
We have a few more slides before questions.
So basically, we just briefly describe to you some of the research areas where we cannot go into every single faculty research areas. Each faculty has more than one area. Where we just give you kind of a few snapshots of those areas we are currently working on. So next, since I'm the graduate program director, I'll just give you some of those information you may need along the way when you apply for other programs. And our office admission has a very good website to give you all the details. Basically, all the information I had here, I grabbed from your website. It gives you very detailed information about what you need to have in your package to complete your application. Only if your application is complete, is get to pass on to the department. We have a chance to look at it and make decisions upon it. So so basically, you have had all those components. I believe you're already familiar with them. Have the personal statement, your CV, your letter of recommendations, and your official transcript and degree. And when you in the application process, if you just have a quick review from us, you can submit unofficial transcript and degree. But when you are in the final stage, you have us to upload official transcript and degree you obtained. So our official GIE requirement for verbal is 156, and analytical is 4.0. And I think everybody here in this webinar, you would not need to worry about your quantitative, but those typically admitted in our program, we did not set it as a criterion, but those enrolled in our program typically had about 165 and above, and that's typically what we admitted students have those scores. So I also list those total score, and depending on what type of exam you took, you have different minimum cutoff. We also accept the IE, LTS, and PTE, the substitute for total. If you took those exams and have a score above the minimum here, we also take those. And so typically we start to make decision from early next year until April, because the funding continues to come in. We basically admit students on a rolling basis. And so be patient with us. If you don't hear from us in February, as long as we did not email you yet, we're still under consideration. Just be patient with us. But sometimes it indeed takes some time for us to know what is the funding situation report, to know how many students we can admit for sure. Don't want to give up so easily on you. So just be patient with us. We appreciate that. So I list my phone number and email there. Anytime you have questions, just email me or call me directly. I'll be happy to chat with you with any details or questions you have. Yes, I think that's
That's the last slide.
one more maybe. That's just check.
Yeah.
So this is our building and the Material Research Center buildings. And if you came to the Albany area, welcome to stop by to help our faculty and the students to either anytime. You're welcome.
Okay, and now we'll open this up to questions. If you have any questions for anyone here, please just type them into the chat box. We have a few people now.
Okay.
I don't know of anyone testing mode 2 fracture toughness. It's like really specific, but I mean, we could. We have the capacity to. We just got a very new instrument. Yeah, but it's one of the ones that's not just this.
This is 1, 2, and then 3. I think that's.
So that's an obvious.
We learned
That's
about that.
one. And that's the only one anyone ever.
Most people use.
Okay, so here's a good question. How does the process of selecting your area or field of research work?
You mean for the, I presume, Kendall, you mean for the graduate students specifically? Right, so do you want to answer that question? Or, really, it's up to.
So basically, you don't have to decide what project or which professor you can work with before you apply or before we make an offer to you. Basically, we make decision based on your credentials and based on likelihood, we will find you a good match. Okay, so but you don't have to make decision beforehand.
But you are free to do so if you.
Yeah, you are free to do so. It sometimes works that a particular faculty and student know that they want to work together, and that can be sorted out even before you start. But you could also come here without a particular advisor in mind and pick somebody once you've arrived. In your application materials and in the essay, oftentimes people will mention who they might hypothetically think about working for.
Yeah.
If that helps.
So when I'm looking for applicants, I definitely looking for your background because we want you to come here, also want you to be successful. We want to make sure that some broad range of project your background can work on.
If I may add to that, I think one of the things is that if you know what you want to do, that's always great. But I don't think you should be worried about thinking that your experience is something that you have to be tied to, right? Experience is always a positive. It doesn't have to be it's certainly not a negative. I've seen people come in here and succeed tremendously after having shifted large amounts. We get people from all kinds of backgrounds. The bulk of our students tend to be material students, but we also get students from math, physics, chemistry, and other disciplines, right? So the exposure that you have had shouldn't be something that you should feel that you are tied to, and you have a complete freedom to come here. We guarantee funding for students who have been admitted. So if you come in and you feel that you want to speak to people, shop around a little bit, take your time to take a decision, we are completely supportive of that.
Yep. Okay, we're just waiting for a few more questions to come through.
Yes, all applications will be considered. In an ideal case, your GRE scores should meet the requirements. If they don't, I think in some extenuating circumstances, there's a possibility that we could request a waiver from the Office of Graduate Education, but there's no guarantee that the waiver would be granted.
So I add a little bit to that. If you are an Nico your English is good, and if you are strong in some other areas, we'll not just look at those testing scores, look at your package as a whole to see where your strengths are. And if there are some one or two areas slightly weaker, we will do our best to make you successful through the system.
Yeah, and as faculty members, we are looking for students who can perform well, and so sometimes if the things that we look at tend to be much more weighted on what your fundamentals, what we believe are reflective of your fundamental abilities in the training that you have and the things that you have done, things that you have demonstrated clearly that set you apart from just a run-of-the-mill student, right? Because we tend to attract students who go beyond just the things that regular students would do, right? So if you find that you're in a situation where maybe you're worried that you're rattling the bar, or you're kind of close to the bar in some of these generic test scores, then we may reach out to you to get additional information, like Professor Wang said, which can bolster your case, which we will use as a proxy to demonstrate to us that you have those requisite aspects that might otherwise be partially reflected by those particular scores.
Indeed.
This guy or this lady has like four or five papers.
That's very good.
Yeah.
And that's certainly evidence of analytical writing skills.
Yeah.
So,
Good question.
what qualities do successful graduate students in your department have? What makes a student stand out in his application?
So, typically you have to, the GPA and GRE, those are the kind of hard numbers. We have some minimums you have to, because if you are, lower in GPA, especially in areas will be critical for our courses and research, for example, your math and materials science related classes. Well, not just look at GPA as one number, also look at your transcript to see, whether you're going to be able to successful taking our classes and doing research with us. So English is just make sure you're able to come here and communicate with the already written, because you have to publish papers and do research with others. And other aspect we look at also will be, have you done research before, and do you have applications and awards, and those are the other things we look at it. And I think, so usually since we are engineering school, we are material science, we are typically looking for students with a strong math background, and physics and chemistry. Those are the courses we're looking to make sure you have a background. You come in, you're able to take our classes and be successful.
Yeah, and just go on.
Yeah, and the one thing is like, if you don't have very good GPA, but your rank is very high, right? This is the rank.
Yeah,
This is the rank there. This is very helpful.
particularly international students.
Yeah.
The ranking matters.
Yes.
Because different schools have different GPA,
Exactly.
scale. Some are very tough GPA, GPA not inflated, and they have very low GPA, but it's the ranking you have in your class or in your school going to tell us where you are, and not absolutely that. If you can put that one in your CV or somewhere in your application indicate what's your rank in your class or in any comparable group, which is much better than just number itself.
And if I could just add a last aspect to something that Boris asked, I would say, it's true, you ask different people and you get different opinions on very specific things, right? Like I might in particular situations look for students who have done a little bit of research, or I might look for, when I have a project that's related to polymers, certain experience may stand out to me. But like in most places, there are going to be a certain set of things that make you unique, right? All places are looking for talented and motivated students, right? That's the bottom line, and that's true, right? So whatever are the aspects that sort of make you stand out is something that that if I were to, when I'm looking for an application, I tend to look for things that make the students distinctive, right? Have you taken the initiative to do an REU in a particular semester, right? So So that's a research experience for undergraduates, right? Did you do something? Did you go above and beyond in a particular project, right? Are there certain aspects of something that you worked on that distinguish you and make you particularly suited for a particular aspect, right? So finding out things that make you unique in terms of certain capabilities are certainly things that I would emphasize, particularly related to prior research experience.
Yeah, and you have the opportunity to do that and to communicate those concepts in the essay portion of the application that you submit. And then, of course, if you had a great research experience like Chaitanya was describing, a letter of recommendation from the faculty member that you worked for, a strong letter, would also helps your case quite a bit.
Okay, we have a few thank yous. You're welcome.
You're
welcome. You're welcome.
Especially some of those from Asia.
So does anybody have any questions about, I don't know, for the graduate students in terms of the nature of the program, in terms of the sort of things, just the administrative hoops that you have to jump through, qualification, average times, things like that, what the students do?
Good question.
Do we have a preference between master's and PhD applicants?
So at the current, we don't have preference, but at the institute level policy, and we cannot use institute funding to support a master student. So if you come in as a for master degree, we have to talk in detail how to support you through the process. That's not automatic. For PhD, it's almost guaranteed. You know, when we decide to admit a PhD, we already have a plan in place. The combination between external funding and institute funding to guarantee you through the system if you are passing every stage of your classes, your qualified exam, your candidate exam. If you've done your part right, the funding is more or less guaranteed through the process. But for masters, that's not guaranteed. And we have to talk to see whether you can fund by yourself, you can fund some industry money to fund your master program, or some other combination. That is not automatic. I'll talk in detail.
What if I see I'm an applicant, I don't care about funding. Do you have a higher like a requirement on like a PhD applicant, or like you have some like a different level of requirement on master student or PhD student, or you have a high expectation on the?
So if you are above the institute minimum,
Yeah.
there's no difference. But if you're below,
Yes.
I still have to go through justification for the
Even for master
yes,
students.
yes. I still have to write the full
Okay.
justification for that.
Yeah, we have a basic standard.
Okay.
So,
I see.
Okay, are there any other questions? We also have two graduate students here who may be interested in answering anything about what their experience has been.
Anything about like the student life you might expect when you get here too.
and despite the pain look on their face, they're going to be honest.
It depends. So I'm actually in two research groups, one of which I'm the only PhD student. We have a couple of like masters for like 1 year, that kind of student. And in the other group, there's five PhD students.
I would say the range is
3 to 4.
well, that's close to the average, but the broad range could be anywhere from 2 to like 10. Right?
Yeah. Yeah, so it really depends on the group and the funding situation.
We don't have any 35-person group.
Yeah,
Yeah.
we don't have any.
It's a small department, so.
Yeah, we don't have any departments within the department.
And there aren't too many postdocs either.
Yeah, so there's a couple of.
We have a few postdocs.
So in answer to Shin Chen's question, we have, so Professor Linda Sharda specifically works on polymer deposits and nanodeposits. Rami Osik does a little bit of that as well. Dick Siegel in the past has at various points worked on nanodeposits. So we have various people who work on that. But if you were to immediately ask me to name somebody and you would tell me to name only one person, I would say Dr. Prakash.
Okay, Chris has a question.
I mean, it's supposed to be a 4-year program. And
So, yeah.
it can be 5 years.
I would
But
say
not
the
long.
average for this, as you're probably aware, Chris, there is no fixed rule about when people graduate. It depends sometimes on the thesis and stuff like that. But to give a practical answer to what you were saying, just to echo what Dr. Palermo said, anywhere between 4 to 5 years is the average for the department. And in terms of the graduation rates, I would say in some sense what you're effectively asking us and what Noor is also asking us is related to the qualifying exam process, right? So maybe we could just briefly describe that, and I would say for the students who make it past the qualifying exam, it's close to 100%, right? It's pretty much 100% at that point of people who, once they made it past the qualifying exam, it's pretty much it's close to 100% of the people who get their PhD.
I'm making that like 2 students of their experience, a little bit about your
Yeah.
experience you had about 25
Yeah, and maybe describe a little bit of the structure of
Two of my committee members are
Well,
here. They can probably tell you more. It's a 2-hour oral exam on the fundamental courses that you take your first year. So you take the majority of those courses your first semester, and then in your second semester here, you study a lot for those exams, and you form study groups. And I think that was actually one of the good bonding opportunities with the other students was forming the study groups for our qualifying exams. We all, once we've got through the qualifying exam, we look back and think of those as good times.
Yeah.
But, once you're done with it, but yeah, there is a lot of studying because it's a 2-hour oral exam with 4 professors who are grilling you on the fundamental courses.
You get 2 chances,
Yeah, you get 2 chances for the oral exam.
and you don't have to retake anything you pass.
and just to clarify, there is no, so we consider, we don't have a written exam. You have, as Mike mentioned, 5 core courses that you are required to take if you're in the PhD program. These are structure and bonding, electronic properties, mechanical properties, thermodynamics, and mechanics. And since you're giving exams in those classes, we don't require you to take another written exam at the end of it. But we do have a requirement related to the average GPA that you have at the end of before you take the qualifying exam. So you need to have a minimum B average in order to be eligible to take the qualifying exam. That's 3.0 on 4.
So I think we missed one question that was on here about graduate student living situation.
Yeah, we were getting there. All right, so it varies. Graduate students tend to live in apartments that are near campus, and so there are a lot of opportunities just to move into an apartment in a neighborhood. You'll be like in a building with 2 apartments and a part of a neighborhood. And then there are also a couple of apartment complexes. There's RPI's City Station.
Where Mike's, for example, and Mike's.
I stayed there for 2 years. Yeah, and then I moved out last year when they converted some of it to undergraduate housing. Yeah, so there's that option. There are many apartment listings.
Yeah, I recommend moving into a neighborhood. It's nice.
Yeah.
Yeah, so I have the impression there's a variety of options, right?
Yeah,
I mean, so some of the students who come in the first year sometimes will go into the housing provided by RPI, it's not required. Others, but housing is clearly very cheaply available.
Yeah, oh yeah, the rents are real low.
Which is nice.
Yeah.
That you get a lot of stuff.
Yeah, the cost of living here is not the same as New York City.
Yeah.
It is much less to live here. We have a question, the final decision on applications. I think you said February, March, April. That's
Yeah, so
But on a rolling basis.
Yeah, we do it on a rolling basis and somewhere from late January until early April. So we do it on a rolling basis. And also, there's another question about the masters. Okay, so if you take a master's in the US, basically the rule of thumb will be you cannot use the same credit for both degrees. If you cannot use the certain credit for your master degree, you can transfer here. But if you already use it for your master degree, you cannot use it.
So basically.
Yeah, that's basically the rule of thumb.
You just like know that. Sorry.
Yeah, you cannot stop it. You cannot use the same credit for both degrees.
So in most likely scenario, you would take the 5 core courses again.
And somebody would like you to repeat those courses.
So the 5 core courses are structure and bonding is the first one. So the first semester basically is structure and bonding as one course, mechanical properties as well as thermodynamics. So you have 3 courses in the first semester, and then the spring semester before the qualifying exams is electronic properties and mechanics. Those are the 5 courses in total. And just in regards to what Kirsten answered, do you guys want to talk a little bit about Troy or just what it's like in and around the area?
Yeah.
People might have questions about it.
Yeah, so RPI is actually really well known for having its own rich active culture of things to do. We have literally hundreds of clubs. But then if you want to become a member of the Troy community at large, there's a lot of growth going on downtown in terms of an art scene. There's so many restaurants. All the food is so good.
Yeah, I'm actually really impressed by given the size of Troy, like how high above their weight they are able to punch in terms of how good the restaurants are.
Yeah.
I've heard recently that a lot of restaurateurs from New York City, because they can't afford the high leases, they will move up here, and so that's one reason why the downtown is flourishing so much in terms of the food. There's a lot of good food downtown.
Yeah, they're making it into New Brooklyn.
The funny thing is that the restaurants, food is good, but they look kind of like regular,
Yeah,
right?
Yeah.
They don't look like Michelin restaurants.
Oh, Kristen went to school in Albany.
At this point, I would say Troy has more culture and is safer than Albany.
Public transportation.
It's real good. Also, you get free public transportation
With
with
your RPI.
your RPI ID.
Okay, so if there's nothing else, I think we'll thank you all for joining us.
Thank you.
And let us know if you have any other questions.
Random question.
Yes, he used to be, he just graduated from here, right? So he went to this.
Yeah, he is in Professor Big Boss group. He
Right.
was in my class. He was one-on-one advising.
Right, and he was in my assistant cost center.
Yes.
We got someone here.
Yes.
Yeah, I remember Paul.
We know him very
You're
well.
welcome, Dominic. Yeah, undergraduates can apply for a PhD.
Of course, yes.
Yes.
The bulk of our students tend to be people who come directly from an after getting their undergraduate degrees. I mean, you have to get your degree, of course. But the bulk of our students actually are come directly from undergrad.
All right.
All right. Thanks, everyone.
Contact us with any questions.
Oh, thank you.